Okay, this is the third in our series of talks in terms of TMDLs. In terms and what we're going to talk about here is models and modeling, and we'll use the Bush River TMDL as an example of that. And why do we want to do models and modeling? Well, simply put, a model is a representation of reality, and the fact is that it's much easier to be able to, or it's cheaper to model something than it is to go out and really get monitor it and get really representative data for the an entire watershed that might be in TMDL. So you would create a model that's based on your existing data. For instance, you might have 1 or 2 water quality monitoring stations within the watershed, and then you would then calibrate your model so that it looks more or less like the data that you get. Can you repeat some of those data? And if you can, then you can perhaps try and make some inferences upstream of that model. For instance, who contributed what to this water quality or this poor water quality thing. Okay, so what's a model? It's a description of a physical system that would perhaps predict or explain a system. So in this case, really what you're doing is you're taking a model, developing it, and trying to match it up with previous data that you have. And then you're, from that previous data, if it works, if you've got a good match, if you've got a good R-squared between your data and the model's data and the empirical data that you have, you can say, well, based on that, this, these things might have contributed. Sometimes you have a model that says, well, what if we have a flow of X, what are we going to expect down there? What happens if we have an extreme condition? So there are different ways that you can use the model. They can explain the physical behavior of systems, what happened, how does it work, which we would want to look at in a TMDL and predict things in the future, what ifs. So bottom line, they're cheaper. You want to use the KISS principle. My dad used to say, well, you don't want to fire, you don't want to use a pea shooter to shoot, to fight a lion, and on the other hand, you don't want to use a tank to go up against a mouse or something like that. So you want to decide the appropriate tool. You want to use the least sophisticated tool or the most parsimonious tool that you can to deal with the question at hand. It doesn't help if you invest $100,000 in modeling efforts to deal with a problem where you've only got, say, $10,000 worth of resources. So you're using KISS, the KISS principle, and always remember that you're also using the garbage in, garbage out principle. If your assumptions and your data are garbage, you can guarantee that your model is going to come out garbage. Hopefully, when you're doing your year-end project, you're going to kind of see some of the same things. Hopefully, you can see, well, I changed this parameter just by this much, and off it goes. So I think, and I've done a little bit of modeling in my life. We modelers kind of tend to say, well, let's tweak this parameter, just tweak it up or tweak it down. Oh, that makes it look better. But when that makes it look better, then this thing is out of kilter. Well, let's tweak that. And you might have 20 or 30 different inputs, and it becomes a little bit difficult. Now, I've got a few lists of different kinds of model types and stuff. I'm not going to dwell on that too much. Empirical versus mechanistic, deterministic versus stochastic or probabilistic, etc., etc. There's a nice, in your notes, there's a nice picture of the different kinds of water quality models. But the kinds of freight and transport models that I wanted to talk about very briefly was there are two that sort of I've been familiar with. One was HSPF, Hydrologic Simulation Program in Fortran, HSPF, and SWOT. SWOT is one developed by folks out in Texas. But these water quality models first start, the core of them is the hydrologic part of it. So hydrologic, what is that going to be? Rainfall, runoff, infiltration, interflow, that kind of stuff. You start with that. You then go on to sediments, okay? Erosion and sedimentation, because your hydrologic processes are going to do that. The more overland flow you have, the more runoff you have, the more erosion you might find. And then the more erosion you find, that's where you're also going to then start to be able to look at some of the more other constituents. You know, erosion might be erosion of organic materials, soil, things like that. Over here you'll have a look at turbidity, nutrients. Of course, you have runoff, you're going to see pesticides as well as nutrients. And conservative elements might be like something like chlorine. You know, you tend not, once chlorine is in solution, it tends to kind of stay in solution, so you can use it a bit as a tie element over there. But HSPF is mechanistic in terms that it tries to look at these processes and tries to be as close to these processes as possible. Again, it's just a model, it's a representation of reality. You know, the more we try and explain a phenomenon, often, you know, we run into other problems. So it's mechanistic, it's deterministic in terms that of it doesn't have a stochastic, you know, it says, well, if your flow is this and these parameters are like this, your pollutant of interest is going to be X milligrams per liter. It's deterministic in that sense. But it also has some empirical elements. For instance, it'll make use of elements of the SCS rainfall runoff equation, which was an empirical model. I think it makes use of some of the old USLE soil loss stuff. So again, I'm not really deeply familiar with the model anymore, but it has various elements. You know, it might just have an equation that's thrown in there based on empirical evidence and say, well, you know, this literature says that this particular contaminant varies when these things happen by this amount. Okay, so that's HSPF. There's a nice little picture of it. You can break it up into different streams, into different stream reaches where the streams come together, and you can go to town on this, and you can do an awful lot of cool modeling. The next picture in terms of the model output is that you might, for given rainfall, you would be able to calculate the given runoff in a particular place, sedimentation, and then calculate for those given conditions maybe the contaminant load that you're going to look at. And then you'll see in this picture, you've got the red line which is indicating the contaminant load, and you can see in terms of non-point source pollution, that contaminant load is very much going to be dependent on your weather-related events. And then you can see your empirical or your actual data are those little round dots there, and you're saying, well, you know, essentially what you can do as an XY plot is, this is what my model predicted, or this is, yeah, what my model predicted, this is my actual samples that are out there, and hopefully you get a sort of something like this with a high R squared value. R squared is basically going to be percentage variability of X over or as a function of variability, percentage variability of Y over variability of X. So that's basically what your R squared. In other words, an R squared of 0.5 or 50% might suggest to you that for a 1 unit increase of X, you'd have a 50% increase in Y. So that'll kind of say the model explains about 50% of the variability in the actual watershed. So that's what you've got. But this picture, this next picture in Novotny that I got from the textbook book Vladimir Novotny, I think is really interesting, is that this is watershed size and error, essentially possible error. Okay, so if you model a watershed just for hydrology, your relative error propagation is you know, it's not too bad. You know, you can get some pretty cool stuff. But now, because your sedimentation and erosion are dependent on your hydrology, well, you get another relative error propagation. First of all, it's dependent on your hydrology error, and then you've also got error in, you know, your basic sedimentation calculations. Well, now you're going to start looking at things like phosphorus and metals. Phosphorus and metals, if you remember that the life cycle of phosphorus is related to soils, for instance. So phosphorus and metals, it makes sense that it's going to be tied to your erosion and sedimentation, which is tied to your hydrology. You're getting the picture now. Now you think looking at nitrogen and organic chemicals, and all of a sudden, okay, well now this is dependent on this. Well, nitrogen has got these 7 oxidation states. So, you know, has it denitrified? Has it gone back up into the atmosphere? Has ammonia had more, you know, is there a source of ammonia that's converted more to nitrogen that we haven't accounted for in the model? Organic molecules might have very, very short half-lives. So we get into even more uncertainty. And of course, by the time you get up here, when you start to monitor your microbes, you know, bacteria, fecal coliform bacteria, all bets are off, you know. So you might know what your bacteria are in the watershed. Up here, you might have a measuring point, but good luck trying to predict how much is over here if you've, say, got a little stream coming in there, even when you don't have a stream. You know, you can calculate bacterial decay rates, and there are all sorts of models that have been founded, and a lot of the data might be in a lab, and they say, well, this amount of sunlight and this and that and the other. But it gets to be very difficult. And so the take home really that I wanted to give you, I don't want to disillusion you, but the error propagation, or the potential error that you're going to find in models, is huge. And what you often find with modelers, especially if they are enamored with their own models, and most modelers, you know, you develop a relationship with this thing, and, you know, you're tweaking the numbers all the time. Most modelers, I think, and myself included, I suppose, we fall in love with our own models, and we start to believe them, and we forget that there's this error. Now, the margin of safety is supposed to kind of deal with some of that error, but I think sometimes when we model, we have unreasonable expectations of them. And when you're talking about the public, and you have these sort of guys with the thick glasses and a lot of pens in their pockets, and they start talking and looking very smart and very wise, you know, how much, I'm sure they believe their numbers, but we just need to understand that those models are really subject to error propagation. a few thoughts on the historic TMDLs. I'm going to take you through the Bush River TMDL very quickly, but you know, the Bush River TMDL did a full. He used this guy called Andy Miller. He's a very smart guy. He's a water quality expert, and he used HSPF to do this TMDL in the Bush River. I think at 215 square kilometers. And I think he did a great job with the tools that he had. You know, I don't know how long it took him. I think it probably took 2 to 3 months. So you can imagine a highly qualified guy, 2 to 3 months to do some modeling there. And he produced this very detailed Bush River report. It was one of the first in the state. 2003, we started looking at slightly less sophisticated models like the water character relation system. They used some estimation spreadsheets. It was still pretty complicated. But Allison Creek, for instance, they just went ahead and did a load duration curve. Now, load duration curve can tell you a few things, and I'm going to actually, the next talk that I'm going to do is going to be talking about load duration curve. But, you know, that's not going to tell you all that much. But they've gone from very complex to fairly simple. I haven't looked at TMDLs recently, but I suspect they continue to be simple. And if the consulting companies are doing them, they're turning them out like cookie cutters. And not that much thought is going in. They're basically meeting regulatory demands, but not actually making the water quality any better. Okay, so let's go ahead and look at the Bush River TMDL in the context of what we've already seen. First of all, what the TMDL plan does is it estimates. So go ahead, I sent you this document over here. So you should have that handy, and we'll walk through it. And go from there. But what's a TMDL document supposed to do? It estimates the total amount of pollutant that can, and we've done this already, that can be assimilated by a receiving water body while still maintaining the applicable water quality standards and criteria. It includes a margin of safety, and it estimates the relative sources of the contributions. Okay, there, you know, your modeling and judgment comes in, and then it allocates reductions. Wow, so that's kind of interesting. Okay, so let's look at Andy's work, the TMDL. You can see on the first page, or before the first page, he kind of provides a bit of a summary of what the thing is. Then he goes in and kind of looks at the whole Bush River, what the land use was, forested, cropland, urban, because basically from those numbers, if you think back to your SCS number, you can estimate more or less the amount of runoff that you're going to see from each of those land uses. And then you can go, he broke the Bush River up into about 16 or 17 sub-watersheds. And for each one of them then, oh no, wait a minute, it might not have been as many. He's looking at the lower bush, mid bush, and upper bush. He happened to have good water quality monitoring station data for these, okay? So, but in this case, he broke it down into bare rock, deciduous forest, emergent. So that would kind of give you an indication, perhaps also of a more detailed land use where you could estimate your runoff from those things. Talks about the water quality standard. So on page 5, your fecal coliform standard is 400 CFUs per 100 mils, and you know it's impaired because the Bush River exceeded that. More than 10% of your samples exceeded this particular criterion. So he goes on and he talks about point source. There was a point source at Newbury, the water and sewer, Newbury County water and sewer. the Bush River plant and the Lawrence County, the Clinton plant. And so he knows how much flow comes out at what concentration, so he's got that down as well. So here it starts getting tricky. He talks about wildlife, what my assumptions about wildlife are. And so he talks about that, talks about concentrated animals. That's animals that they keep in pens and feed and then sort of clean out there. Grazing animals now, they went out and did a count. Well, they estimated them from, I think, the ag census data, how many cattle, dairy cattle, and then made all sorts of assumptions. Okay, here he had a little spreadsheet, and you can get these spreadsheets from the EPA, and it really, you can basically, based on data from different places, you can estimate how many fecal coliforms a cow produces in one day. So produces 120 pounds of manure, and then 8.37 times 10 to the 8. Okay, so we're already saying, oh, you know, you're making an assumption that each cow produces 8.37 times 10 to the 8 rather than 8 times 10 to the 8 plus minus, you know, whatever it might be. So they've got different things there, and basically you can, with HSPF, you can model based on maybe your location of where these animals are, how much of that material or how much of those bacteria get into the water after sun degradation in the sun. So where do they lie, where on the landscape, and things like that. Again, you're making all sorts of assumptions. We're on page 6. Another non-point source pollution or non-point solution source would be failing septic systems. And you're kind of looking at the literature and saying, well, for this region, you know, we've got so many homes served, and of them a certain percentage is failing. And then based on that, we've got data that, you know, maybe this literature saying this is how much a failing septic system will deliver to the system. And then there's 3.2.6 on page 7, other unknown sources. So remember that graph of error propagation that we were talking about? Well, kind of that's where the rubber hits the road. You know, there's the rub. So he goes ahead and he talks about the model selection, and he calibrated it for observed and modeled stream flow, and look how beautifully it calibrated out. And then he looked at water quality calibration, compared his numbers there in page 9 and 10, figure 4 and figure 4b, water quality calibration plots. So he's looking at his actual data that he found versus what the model spits out. So he carries on with this stuff. He basically comes up with, for the mid and lower bush, estimated non-point source loading rates for existing conditions. So, excuse me, the model's telling him, okay, runoff is going to give us so much, direct inputs to streams from animals is going to give us so much, leaking and overflowing sanitary systems is going to give us so much, and septic systems. So, you know, you're talking numbers, those numbers over here, 10 to the 14, 10 to the 12, 10 to the 11, and stuff like that, is E. coli per day passing a particular point in the stream. So, again, it's pretty impressive what HSPF does, but based on all of the assumptions on, you know, your hydrology, your land use, the amount of animals and where they are, can you take this to the bank and say, take it to the court and make people reduce, you know, or stop doing certain things like grazing their cattle in the streams or something like that? And what you can see on table 9 is here's your Bush River TMDL. He breaks it up into two, the mid Bush River and the lower Bush River. You'll see the lower Bush River obviously has more bacteria, obviously, because it's got some from the upper part of Bush River. But your waste load allocation, remember, that now comes from your point source polluters. Your load allocation, listen, look at this, 1.4 double, I'm not making fun of Andy, but I'm just saying there's an implied accuracy over there, 1.4885 times 10 to the 14. So that's an implied accuracy which I'm not going to buy, all right? There's an implicit margin of safety. I think HSPF might have a system where that's implicit. And so your TMDL is your waste load allocation plus your load allocation, and there you can see on table 9 what his TMDL for the upper and lower Bush River was. So he's saying that no more than this amount of bacteria may go past this point. Talks about his waste load allocations. Now, here's the cool part. He's saying that in the mid and lower Bush River, we've got to actually reduce our loads, our non-point source pollution loads, by 16.6 and 16.8% respectively. And because we're exceeding that on average by 16.6 and 16.8. So the assumption and the hypothesis is that if we can only reduce this by 16.6%, we will no longer have any TMDL or any exceedances of the 400 CFU per 100 milligram criterion. Again, I find that somewhat difficult to swallow. And again, I'm very much a pessimist, or not a pessimist, but a skeptic of this. And again, with all due respect to Andy, because I think he's a great professional, and this is one of the very first ones. Have a look at the implementation. The implementation over here is extremely vague. So what you're doing as the planner, you're saying, here's the plan, and then you're giving it back to the EPA. The EPA says, okay, here's the plan, give it to some sucker who's going to go out there and implement that. Who are you going to give it to implement? You're going to give it to the Soil and Water Conservation District. Well, they could speak to the farmers, but the farmers might say, well, you know, it's not us anyway. But, you know, you can give us the money anyway and we'll use it for putting in fences and stuff like that. Again, it becomes really, really tricky. You're going to have to be politically astute. You're going to have to manage your money very well. And I think the Bush River initially got $300,000 to $600,000 for 215 square kilometers. And you can imagine, you know, if you had to go sample that today, it's still going to be about as bad, if not worse, than it was when it was first considered impaired in the early 2000s. So again, the take-homes over here for you, especially sort of in this water quality business, or if you're meeting people in water quality, is just because somebody has this very, very sophisticated model, often that model makes many, many assumptions that you need to be aware of. I'm not telling you to discard modeling results. I'm telling you to be very wary and very, very careful. Be very careful of modelers who tell you that you don't need to go out and take samples because he's got every confidence that his model works, or she. Again, all I'm trying to do is paint a realistic picture. I think the regulators are at the point, in about 1994, 95, man, the regulators that came onto the TMDL systems, oh man, this is just the greatest system, we just have to do this and this and that. And I think they're beginning to look at the whole system right now and say, yeah, that wasn't that easy to implement, because really you can't go, you know, non-point source pollution often is very diffuse, and even if you can define non-point source pollution, you can't always address it. Now, I haven't really spoken, well, actually I'll just put that in something else. But anyway, so that's on models and modeling. Hope this has helped you. Hope it kind of helps you in your homework, and then also kind of thinking through your end of year, end of class exercise. Thank you very much, and talk to you in a bit.